In our last lecture, we were having an introduction to the basic concepts behind the image and video coding. We were discussing about certain fundamental aspects, and today we will be covering the lossy image compression technique. I mean, we had made a mention of some of the techniques. So in lossy image compression techniques, what we are going to discuss today is about the discrete cosine transform, or the DCT as it is known as. Now, before we can begin the topic of the specific transforms like the DCT, okay, let's first have a basic concept about what we are essentially going to do by the process of transformation. So as I was telling you in the last class, that there are two basic purposes behind the transformation. Number one, that the transform coefficients, means in the transform domain we are going to have the coefficients which are decorrelated. And then the second aspect that we are going to exploit is that the transform coefficients are going to have an energy compaction capabilities, in the sense that the energy will be contained, the bulk of the energy of the signal will be contained by only a few transform coefficients, so that an efficient compression can be reached by truncating those coefficients which are not carrying any significant energy. So that's the basic philosophy with which we proceed for transform coding. And as I was making a mention, that some of the transform coding techniques, okay, that has emerged, because basically in order to have a decorrelation we require the usage of the orthogonal transforms, and in that category we have the discrete Fourier transform, the discrete cosine transform, the discrete Haar transform, Hadamard transform, then KL transforms, and also the recently investigated ones, that is to say the discrete wavelet transforms. Okay, so we have so many techniques with us, but for certain reasons the DCT, the discrete cosine transform, happens to be quite useful, okay, in the concept of image compression, and it has been adopted in the image compression standards which were proposed. At least the first versions of the image coding standards had made use of the discrete cosine transform. Now essentially what we are going to do for an image transformation is that we have our basic signal as S of n1 comma n2. Okay, so this is the intensity, this is the image intensity at the coordinate position n1 and n2. Okay, so it's basically a two-dimensional signal as we were mentioning. Okay, and what we want to do is that from this S n1 n2 we would like to transform it to a transform domain where we are representing the signal by capital S, okay, and the transformed coefficients indices we are using as k1 and k2. So essentially we have to make a transformation from S n1 n2, that is to say the original pixel domain, or which is in the spatial domain, we have to transform it to the S k1 k2 which is in the transform domain. Okay, now what we want to do is that in the transform domain we want to do the quantization, and we want to do the entropy coding on that, and then want to send those coefficients over the channel. But so that will be done at the encoder end, that is converting from the spatial domain to transform domain, and then quantization and encoding everything in the transform domain. And at the decoder end, just the reversal has to take place, which means to say that we will be receiving this SK1 K2, and then we will be doing the entropy decoding. We will dequantize it, that means to say that whatever factor we had used in order to divide the transform coefficients, so we are going to multiply those factors in the dequantization process, and then we will be getting back S N1 N2, not exactly S N1 N2, but it will be S cap N1 N2. So what we require is a reversible transformation. That means to say a transformation should be so designed that we can go over in the encoder, we should be able to go over from the spatial domain to the transform domain, and at the decoder we should be able to go from the transform domain to the spatial domain. So it should be, so whatever transformation we should use should be a reversible transformation. Okay. And not only that, if we do not use any quantization, that means to say that we do not have any lossy element in our image compression system, in that case the process of encoding and decoding should not introduce any errors. So that means to say that in absence of the decoder we must have S N1 N2 and S cap N1 N2 to be one and the same, right? Now to have such a kind of, so that means to say that the reversible transformation what we are designed, what we are going to consider, okay, the process of this transformation, it should be completely a reversible process. So whatever transformation we use in the process of its inversion, okay, in the process of inverse transformation, we should not be losing any information, right? So in general, this transformation one can write as S K1 K2, one could express in general as a double summation process. I will be putting the limits of this double summation very soon, okay, and then small s N1 N2, which is to say the original pixel domain or the spatial components of the signal, and then we are going to have a transformation kernel, that's what we call, and let us denote that kernel by a function g. Okay, so g is going to be a function of N1 N2 K1 K2. Okay, everything will be involved in the transformation process. So g, its argument should be N1 N2 K1 K2. Okay, so we are going to have all these things, and what should be the limits of the double summation process? Well, we are considering the spatial domain image. So its indices are N1 and N2. So the variables in the summation process are going to be N1 and N2, and its limits of summation has to be considering the complete image size, right? So if the image size, if we consider that the image is of size capital N1 by capital N2, in that case our N1 is going to be 0 to capital N1 minus 1, N2 is going to be 0 to capital N2 minus 1. In special case where we have a square image N1 and N2 equal to capital N, in that case it should be 0 to N minus 1, 0 to N minus 1 for N square number of pixels. Anyway, so this is what we will be calling as the forward transformation process. Okay, so this should be the general equation for the forward transformation. Okay, and we should be able to design an inverse transformation. Okay, so what the inverse transformation is going to do is to get back S N1 N2, okay, from the transform coefficient S K1 K2, and what we are going to have is that S N1 N2, that should be equal to capital, that should be equal to the summation process, double summation process, S K1 K2 into the inverse transformation kernel, let us call as the H, right? So H is the inverse transformation function, H N1 N2 K1 K2. Okay, so here the summation has to be performed over K1 and K2, so that it should be K1 equal to 0 to N1 minus 1 and K2 equal to 0 to N1 minus 1. Okay, now there is one thing which we haven't mentioned yet. Okay, that's to say that here this is a summation process, mind you, that how many, so what is the computation complexity of this? It's going to involve N1 times N2 number of multiplications. Okay, so if we are considering the order, okay, the order of computation is going to be order of n square, in the sense that if if you say that n1 is equal to n2 is equal to n. Okay. So considering that, the order of computation is going to be order of n square. Okay. And so at the end of the n square computation, what we get? We get one k1 k2 value. Okay. But mind you, in the transform domain, we are going to have n square number of such sk1 k2 coefficients, because this equation one can write for k1 k2 equal to 0 to n minus 1, or rather to say, if you write it in a general way, k1 can go from 0 to n1 minus 1 and k2 can go from 0 to n2 minus 2. Okay, or let's write it this way. So in fact, let's write it as 0 to n minus 1, here also 0 to n minus 1, considering as a square image case. Of course, we are not losing the generality in any sense. Okay. So sk1 k2, we are having n square number of such equations are possible. That's correct. So when n square number of such equations are possible, okay, so that means to say that for each of these n square number of equations, we are going to have n square number of multiplications. So the order of computation that we clearly see here is going to be order of n to the power 4. Okay. So this is a two-dimensional, so that's how it has increased. I mean, we know that for a discrete Fourier transform, one-dimensional discrete Fourier transform, we all had seen, okay, in our digital signal processing courses, that it's order of n squared, that's what we get, but in this case it's order of n to the power 4. Of course, there are many fast algorithms for computation of these transformations. Okay, so those who have gone through the digital signal processing course are familiar with tools like the FFT, the first Fourier transform, which significantly reduces that. Instead of the n square, order of n square for the one-dimensional signal case, you can make it into order of n log n, okay, for the using the FFT algorithm. Okay. So now this is k1 k2, so which means to say that k1 and k2 are going from 0 to n minus 1, right. So in this case also, in the summation process, we are writing k1 k2 going from 0 to n minus 1, and we are getting Sn1 n2. So as we did in the previous equation, even here also it should be possible for us to write down n such equations for each of these variables n1 and n2. So which means to say that there are n square number of such equations which are possible. So this equation that we wrote just now, okay, this is going to be our inverse transform. So we have the forward transform and we have the inverse transform, and we didn't have to write S cap n1 n2 over here, because the transformation that we are using is exactly reversible. So which means to say that we should get back S n1 n2 exactly. So it's not the transformation process which is lossy, okay. It's, remember, always the quantization process which is the only lossy element in the system. And why we are going all this, why we are going through all this transformation process is simply because that in order to have the decorrelation of the coefficients, so is sk1 k2 should be decorrelated, and again, as we said, that few of the coefficients of this sk1 k2 would carry most of the energy. That means to say that having the energy compaction property fulfilled. So now, so given that, so this is the generalized form, okay. Now as special case, okay, one can consider any type of kernel, okay. So like say for example, if this g n1 n2 k1 k2, we have the function, let's say exponential to the power, okay, say if we choose g n1 n2 k1 k2 to be the exponential of j, okay, and then we write it as 2 pi n1 k1, 2 pi n1 k1 plus n2 k2 divided by n square, okay. So if we write that, in that case, what is the transformation that results? So that goes, so that becomes the discrete Fourier transform, because it's a complex exponential kernel basically leads to the discrete Fourier transform or the DFT. If instead of exponential we take a cosine kernel, okay, in that case we get the discrete cosine transform, okay, and there are other transforms also which should be possible. So we did not use anything specific over here, but let's study some of the very important properties of this G N1 N2 K1 K2 which we very often come across. Okay, the first of this property which we quite often make use of and come across is that, just say for example, look at this kernel, that's to say the discrete Fourier transform kernel. Okay, one can write this kernel, okay, as a product of this N1 term and the N2 term. So which means to say that it's possible for us to write it down as exponential. Actually it's customary to write the minus in the forward transformation process and plus in the inverse transformation process. So it is minus j 2 pi n1 k1 divided by n square, divided by n square into exponential minus j 2 pi into k2 divided by n square. Okay, just expressing this as a product of these two, okay, realizes the same thing. But in the process of realization, okay, we get an advantage in the sense that we can implement first a row-wise transformation and then we can use a column-wise transformation. Okay, so such kind of properties, okay, which I just now described, is going to be mentioned as the separable transform. Okay, so this is called as the separable transform. So in mathematical terms, the separability inevitably means that for the case of the separable transform, it is G N1 N2 K1 K2. We should be able to write this as a product of two kernels G1, we can say G1 N1 K1, okay, into G2 N2 K2. Okay, so where in general G1 and G2 could be different functions also, right? So if this is fulfilled, that means to say that we can express as a product like this, we will call it as the separable kernel. Okay, this is a separable kernel. Okay, and we can have a and in a specific case when we have G1 and G2 to be the same function, okay, if we have G1 and G2 to be the same function, then we call this as symmetric. Okay, like you see that clearly in the DFT, you can very clearly see that this 2 pi n1 k1 and 2 pi n2 k2, the function is basically of the form of 2 pi nk by n square. So that's the general form of the function, which is same as that for the G1, which is this one, and for the G2, which is this one. So this is a typical case, an example. The DFT is a typical example of a symmetric and separable kernel. Okay, and likewise the DCT, the discrete cosine transform, as we will clearly see. Okay, I mean just after some time when we take up the DCT, we are going to see that it's going to fulfill the very similar properties, the separability and the symmetric. It's a symmetric and separable kernel. Now let us have a look at this equation. Okay, that's to say the inverse transformation equation. Okay, let's again number this equation. So the forward transformation let's call as the equation number 1, and the inverse transform let us call this as equation number 2. Okay, so now let us have a look at the equation number 2. So what we are basically having is that there are n square number of such equations, right? So it is possible for us to combine this n square number of equations, okay, and write it in a compact matrix form, because after all, if we compute S n1 n2 for n1 n2 varying from 0 to n minus 1 for both the variables n1 and n2, what we are going to achieve is that it's going to have all the, so it's going to compose an n square matrix, I mean, which means to say that n by n matrix will be composed after that. So combining all these different n square number of equations that we get from equation number 2, okay, one can write the, so a matrix form of equation number 2 one can write as we are going to write it as S, and this S is going to be the S matrix. Okay, so that's okay, so we can write for the matrix equation a different color. So this S is the matrix S, okay, which is going to be summation. Here the double summation is for K1 is equal to 0 to n minus 1, and for K2 is equal to 0 to n minus 1, and then this is Sk1 K2 as it is, okay, this Sk1 K2, well, this Sk1 K2 is after all a scalar quantity, okay, but it is to be multiplied by what? H n1 into K1 K2. Now for a particular K1 and K2, okay, this K1 K2 is a variable index that goes within the summation process, okay. But n1 and n2, this n1 and n2 comes from this. So that means to say that depending upon the elements of this matrix, because now this n1 and n2 that composes the index of the matrix elements, okay. So the index of the matrix elements will dictate H n1 n2 component of it, okay. So which means to say that for every value of K1 and K2, for each K1 and K2, we are effectively going to have a matrix, right? We are effectively going to have a matrix whose elements would be given by H n1 n2, right? So for a particular value of K1 and K2, keeping K1 and K2 the same, we are going to have H n1 n2, where n1 and n2 will decide the matrix elements. So using that, one can write this H K1 K2 also as a matrix. So this is going to be a matrix, and this is H K1 K2. So just to avoid the confusion, let us write this as a scalar quantity, S K1 K2. This is a scalar quantity. So whatever I am writing with red is the vector or the matrix quantity. So this is an n by n matrix S, and this H K1 K2, this is also a matrix of dimension n by n, right? Now what is this matrix? We can realize this matrix, okay, using the transformation kernel. In this case, the inverse transformation kernel. Using the inverse transformation kernel, we get this. But after all, this is also an n by n image. In fact, if we write the elements of this matrix, okay, this H K1 K2, we are going to write, I mean, this is the way the matrix will be composed of. That's to say, this H K1 K2, what we are writing, okay, essentially this is a matrix, okay, whose elements would be given by H 0 0 K1 K2. This K1 and K2 is going to be the same for all the elements. So what we are going to have is that there will be n square number of such matrices, okay. So this is one of those matrices for a particular value of K1 K2. So this is H 0 0, the next element should be H 0 1 K1 K2, and like this it goes for H 0 n minus 1 K1 K2, okay. And on this side we are going to have H 0 1 K1 K2, okay. Here it will be H 0 2 K1 K2, and the last one is going to be H 0 n minus 1 K1 K2, okay. Did I make any mistake? H1 sorry yes I mean I just Yeah, it's 1 0 2 0. Yes, because it is the row index. So in this direction, I assume that n1 is changing. That's correct. Fine. Thank you for pointing out this mistake. This is n2 direction. So n2 is this one. This element is changing, and in this case, it is 1 0 2 0, and this is going to be h n minus 1 0 k1 k2. Thank you for the correction. And in this case, the last element is going to be h n minus 1 k1 k2. Okay. Now this is a matrix. Okay, and when we change k1 and k2, so the first matrix is going to be for k1 is equal to 0, k2 is equal to 0. The next matrix is going to be for the other values of k1 and k2, which will be decided by this summation process. So effectively what we are doing is that we are taking this h k1 and k2 matrix. So for a particular value of k1 k2, whatever we get, we are multiplying that with a scalar coefficient s k1 k2. After all, what is this matrix h k1 and k2? It is an image, because S is an image, right? And h k1 k2 is also an image. Okay, but this image is actually a basis image, because this is not an image which is obtained from any camera, or which is not obtained from any natural image. No such source is there for this image, but this is an image which could be realized, okay, by using the transformation kernel itself. Okay, so this is a kind of a basis image. Okay, so h k1 k2 is a basis image, and what we are doing is that this basis image we are multiplying by the particular coefficient s k1 and k2. Okay, so for every value of k1 and k2 we are having a basis image. So how many such basis images we are having? We are having existence of n square number of such basis images. So essentially one way of looking at the whole transformation process is that the transformation process basically tells you or gives you the clue to realize an image, okay, through a composition of basis image multiplied by its equivalent coefficient. So it is an image which you are multiplying by s k1 and k2, a scalar quantity, and then adding it up. And by adding that up, okay, by adding such n square number of weighted images, you are getting the image with which you are working with, right? So this is the basic behind the image transformation, okay, and essentially the discrete cosine transform, which we are going to discuss now, okay, follows this same basic principle. Okay, so which means to say that if we know the kernel, okay, we should be able to compose our own basis images. Okay, but before we go over to the discrete cosine transform or any other or any specific transformation process in general, okay, let's see that in what manner are we going to apply the transformation. Now in this case, okay, both for equation number 1 as well as for equation number 2, we had seen that this n, basically this n1 and n2, which we consider to be the same, so this n is nothing but the size of the image. So it's pertaining to the dimension of the image, so that it's n by n is the size of the image, right? So now what we are saying is that this transformation is applied over the entire image. So if the size of the image is say 1024 by 1024, in that case for the entire 1024 by 1024 we are going to apply this. Now, so what for we are applying? We are applying it in order to get the correlation properties that exist in the image. Now it's a big image, so the property of the image is not going to be the same everywhere. There will be some regions of the image where we will be having too much of details, and there will be some regions of the image where the details will be much less, right? So in that, what we are going to get is that I mean over such a kind of, I mean it's looking at an image with its globality in the sense that we are considering the entire image, okay, and exploiting its correlation properties. But actually speaking, if you consider the image in parts, if you divide the image into small blocks, okay, and try to study the property of the pixels that exists within the block, within those individual blocks, okay, you will be able to see that within those blocks the pixel values would tend to have a more homogeneity, in the sense that there is more of a correlation between the pixels which are within the block rather than the kind of global correlation which we will be realizing using this. Apart from the fact that when we think of any hardware implementation, okay, for a 1024 by 1024 size, realizing a hardware transformation block for this is going to be a Herculean task. So before performing the transformation, okay, we should be able to apply, okay, what is called as the, I mean we should be able to subdivide the image into such small parts or blocks, okay. So which means to say that conceptually we should go ahead like this, that we should have an image, right. So let's say that this is our image, right, and this image is subdivided into this many blocks, so on. Anyway, so this is enough. So this way will be further subdividing, this way also will be subdividing. So to take each of these, so what is this one? This one is a block of image, okay. So if we have the total image size to be n by n, right, and if we make it into total, if we are going to have n square number of such blocks, if we subdivide, if we partition the image into n square number of such block, then each of the block is going to have a size of what? Capital N by small n into capital N by small n, okay. So we are going to partition the image into these many things, okay. And in fact a typical number, okay, that the standard makers had thought of, okay, is to have n is equal to 8, okay, or in some of the recent transforms, okay, they are also using n is equal to 4, okay. So why such small numbers of 4s and 8s, okay? It helps us in two ways. First is that, as I was mentioning about the hardware realization, that hardware realization is manageable with a smaller size transformation. So definitely whenever we are having n equal to 4 or n equal to 8, we can make a hardware block of that, okay, and there is no difficulty in replicating that hardware block, okay. We can do a kind of parallel processing, because if the image is subdivided into such kind of non-overlapping blocks, in fact what the manner in which we have subdivided is by having non-overlapping blocks, okay. So by having such kind of non-overlapping blocks, okay, we are going to I mean we can have a parallel processing, like say for example, if we are going to have n square number of blocks, okay, we can assign n square number of processors, okay. Each processor can do a computation of performing a transformation, a DCT or any other transform for a block of which is just the size small n, I mean capital N by n and capital N by n. Now it's not small n equal to n 8, so I made a mistake. Okay, it is capital N by small n equal to 8, which means to say the block size is going to be 8. So which means to say that as a very typical example, that if we have, let's say, n equal to 1024, okay, and if we have the block size to be 8 by 8, in that case the total number of blocks, okay, total number of blocks that we are going to have is going to be 1024 by 1024 divided by 8 by 8, okay. So it's 128 by 128. What's the number of that? 128 by 128 realizes 16,000, right? 16,000 type. So 16k number of blocks are existing. So still it's a large amount of computation, but remember that in this particular example we have got 1 megapixels. So that itself is a very large number. Okay. Now what we are going to consider is that how to take up the transformation for such small blocks. So yes, as I was mentioning, that computational advantages is one point, and the second is that when by subdividing it into smaller blocks, okay, we are able to use the correlation that is existing within the block, okay, in a much better way. So there is more exploitation of redundancy. The individual blocks of smaller size is going to exploit the redundancy more as compared to a single large mega block type of a thing. We can take the entire image to be a mega block. We are not doing that, but we are having computational advantage. We are also having the the exploitation of correlation in a better manner. So now in the case of the discrete cosine transform, okay, we are going to use the same principle, okay, subdividing into blocks. Okay, before we come to the discrete cosine transform, okay, just a few words about the other type of transforms, and in this connection I would like to make a mention of the KL transform, the Carhonen-Loewe transform, KL transform. Now incidentally, KL transform is said to be an optimal transform, and it is optimal in the mean square error sense. Okay, so what it means to say is that basically in a computational manner, I am not going into the details of this because there is a good reason, okay, because of which KL transform, despite being mentioned as optimal transform, is not used in practical circuitry. Okay, that's because of its bulk computational disadvantage. It's extremely poor, okay, in terms of its computational efficiency, and that's one of the reasons. And because it is image dependent, so you cannot have a readily available kernel prepared. Cosine values, you can readily make it prepared. Exponential values, you can make it readily prepared, but you cannot keep prepared something which is image dependent, where the kernel is to be realized from the image. So as a result of that, the KL transform is not very popular, but essentially what it does is that this also will subdivide the image into blocks, and for individual blocks, okay, of size n by n, okay, we are going to compute the covariance matrix. Yes, we are going to compute the mean, and subtracting the mean from the original block, and then having a covariance, right? So we are going to have that as the covariance matrix, and then we are going to compute the eigenvalues of the covariance matrix, eigenvalues of the eigenvectors of the covariance matrix, and then we are using, so by ordering those eigenvalues, okay, and considering only the first few eigenvalues, okay, and disregarding the other eigenvalues which are not corresponding to the bulk of the energy term, okay, one can have a very good efficiency. But it is seen that by having a transformation like the DCT, the discrete cosine transform, we approach the performance almost as close as that of the KLT in most of the practical images. So since that is the situation, in that case, why don't we go in for a transformation like the DCT, because DCT is after all realizable, okay, using the trigonometric kernel directly. And in fact, for DCT, the kind of transformation that we are going to use is like this, that in this case SK1 K2 could be written as, let's that is straight away, is root over 4 by n square times CK1 K2, sorry, CK1 CK2 into a double summation n1 is equal to 0 to capital N minus 1, again yet another summation n2 is equal to 0 to capital N minus 1, small s n1 n2 into cosine, so this multiplied by, so please note that, cosine pi 2n1 plus 1 k1 divided by 2n, and there is yet another cosine term because it's a separable. Okay, so this cosine term involves only n1 and k1, and its product cosine term involves n2 and k2. So it is pi 2n2 plus 1 k2 divided by 2n, right? And in this case, Ck, okay, is defined as 1 by root over 2, okay, for k is equal to 0, and this is equal to 1 otherwise, right? So that means to say that only the border, the coefficients sk1, k2 which are existing in the borders, okay, have a different multiplication coefficient, okay, as compared to those terms which are there in the middle. For terms in the middle, I mean, that means to say that where k1 is greater than 0 and k2 is greater than 0, we are going to have ck1, ck2 both as 1, so which means to say that this is a straight multiplication by 1 for this term. Now this is the DCT, okay, this is what we are going to use of, and look at this kernels cos and here also cos, so which means to say that if you take this sk1 k2 and take yet another k1 k2, let's say you take k1 prime, you take k2 prime, and you get another transformation like this, and you try to correlate sk1 k2 with sk1 prime k2 prime, okay, and you are going to add it up, you are going to have a value equal to 0, because it's going to be a an orthogonal transform. This trigonometric term is really the tool that gives you the orthogonality in this case. So this is the DCT, the discrete cosine transform, and from, I mean, we start with n by n number of coefficients, and we end up with n by n number of coefficients. We start with n by n number of image or pixels, we end up with n by n coefficients. So this is the discrete cosine transform, and it is seen that the DCT is giving us a performance which is as close to that of the KL transform for most of the images, very close to that, and it has got very good energy compaction capability. So that makes it a real good candidate, okay, to be used for the effective compression of the images. And in fact, because of this reason, okay, this DCT was adopted in the very first image processing, image compression standard that was designed, okay, way back in 1988 or 89, okay, when the first joint photographic experts group, okay, Joint Photographic Experts Group, or what is called as the JPEG. So JPEG, the first still image compression standard, okay, had made use of this DCT as the transform. Now, essentially what we are going to have in the process of DCT is that the first step is to subdivide the image into such non-overlapping blocks of size 8 by 8 or 4 by 4, whatever. I mean, the essential idea is to divide it into non-overlapping blocks. And then for each of these non-overlapping blocks, okay, we are going to apply this transformation, okay. And after applying this transformation, okay, what results? If this is the transformed array, okay, say this is the transformed array. The transformed array also we are going to represent like this, that if we took this to be our in1 direction and this to be our in2 direction, right? In that case, in the transform domain also we are going to take this to be our k1 direction and this to be our k2 direction. So what is this term? Okay, what is k1 equal to 0, k2 is equal to 0. So this is, so this particular element in this matrix. So k1 and k2 is also the matrix that is having n by n number of elements, right? So with k1 equal to 0 and k2 is equal to 0, we refer to this particular element in the matrix. So this is S00. So what is the special significance of this term? You see, when we put 0, 0, when we put k1 as 0, k2 as 0, what do we get? First is that we get C of 0, C of 0. So 1 by root 2 multiplied by 1 by root 2, which means makes it a half, okay, a half of a quantity. And in this case, root over 4 by n square leads to 2 by n. So it's 2 by n into half, which means to say that overall 1 upon n. And what are we getting in that process? We are getting S n1 in 2, okay. And here, this cosine term with k1 is equal to 0 makes it 1. This with k2 is equal to 0 makes it 1. So it is like summing up all this Sn1 in 2 values, just a simple summing up. So which means to say that this leads to some kind of an average value. So this leads to the average value, or it's the DC value. So we call this k1 k2 to be 0 as the DC coefficient. So S00 is the DC coefficient, and all other coefficients will be referred to as the AC coefficient. So this coefficient is going to be S1 comma 0. Okay, so this will be 1 comma 0. This will be 0 comma 1. Okay, this will be 1 comma 1. This will be 0 comma 2. This will be 1 comma 2. Okay, this one will be 0 comma 2. This is 2 comma 0. This is 1 comma 0. This is 2 comma 0. Okay, so this is the way we will be representing, and is this last one. Okay, that's to say that bottom right. Bottom right, it will be S n minus 1 n minus 1. Okay, so if it is 8 by 8, if n is equal to 8, in that case this is S77. S77 is the last AC coefficient. Now, in terms of the frequency meaning the spatial frequency here, of course, this is the highest frequency component. Its highest frequency both in the k1 direction and in the k2 direction, right? So it's in the k1 and the k2 direction. That's what we are going to have. So this So from the low, so all the low frequency components are centered around this region, and all the high frequency regions are in this region. So we will be expecting that the maximum energy will be in this zone, and this will be the AC which will carry much less of energy. Now, how do we pick up the coefficients? To pick up these coefficients, we are going to traverse in this direction. So this is the DC quantity, right? Next we go over to, from 0, 0, we are going over to the next pixel. Okay, so which means to say from 0, 0 we go to 0, 1, and then we go over to 1, 0, then we go over to 2, 0, then we go over here, then we go over here, then we go here. So this is the manner in which we should travel in order to pick up the coefficients, right? So what results is that this process of scanning, what are we picking up? We are picking up the coefficients in a zigzag manner. Okay, so this DCT array, what we get, okay, should be scanned in a zigzag way, right? So this zigzag manner of picking up the coefficients ensures what? That we start by picking up the low frequency components and we end up with the high frequency components. So as a result of that, so and then after picking up these coefficients, what we do is that whatever correlation exists between this way of traveling, okay, even that correlation also will be exploited by going through an entropy coding of the zigzag scanned coefficient. Okay, so the overall block diagram that we are going to have out of this is something of this nature, right? So let's have a look at the overall block diagram. So we can just say that, okay, the first step is that the input is S N1 N2, and then we are going to have the DCT, okay, and the DCT is going to give us the DC coefficient, one DC coefficient and the rest as the AC coefficient. So let's separate them out. So let's call this to be the DC coefficient and this to be the AC coefficients. Now the AC coefficients are actually scanned in the zigzag way. Okay, so after AC coefficients there is a zigzag scanning, and after zigzag scanning these are entropy coded. The DC coefficients also could have been included in this scanning process, but the DC coefficients are treated in a bit of different way. Why? Because the DC coefficient is remarkably different from that of the AC coefficient, but DC coefficient is after all going to pick up a global property of the two-dimensional signal. So which means to say that it's signifying the average intensity, and average intensity is not going to change from one block to its neighboring block. So there is a good degree of correlation between the DC of this block and the DC of the next block. So one can make use of that redundancy factor by encoding the DC coefficients through a differential pulse width modulation process. So it's a DPCM which we can use, and all this DPCM also, the DPCM coefficients also could be entropy coded. Finally, the entropy coder output is going to yield us the bit stream which can go into the channel. So this is the overall compression system. Okay. Oh, I of course missed one block. So let us say that this is DCT plus quantizer. Okay, because I mean, if we are going to achieve compression, then obviously we are going to quantize the coefficients and then use it. So next class I will tell you a little bit more about this quantizer, that what type of quantizer would you use in the DCT, and then we will go over to the other transforms. Okay, thank you for today.